Chapter 1, Relation and Functions. There is no permanent place in the world for ugly mathematics. It may be very hard to define mathematical beauty, but that is just as true of beauty of any kind. We may not know quite what we mean by a beautiful poem, but that does not prevent us from recognizing one when we read it. G. H. Hardy. Introduction. Lejeune Dirichlet, 1805 to 1859. Recall that the notion of relations and functions, domain, codomain, and range have been introduced in class 11 along with different types of specific real valued functions and their graphs. The concept of the term relation in mathematics has been drawn from the meaning of relations in English language, according to which two objects or quantities are related if there is a recognizable connection or link between the two objects or quantities. Let A be the set of students of class 12 of a school and B be the set of students of class 11 of the same school. Then some of the examples of relations from A to B are: 1. AB belongs to A into B. A is brother of B. 2. AB belongs to A into B. A is sister of B. 3. AB belongs to A into B. Age of A is greater than age of B. 4. AB belongs to A into B. Total marks obtained by A in the final examination is less than the total marks obtained by B in the final examination. 5. AB belongs to A into B. A lives in the same locality as B. However, abstracting from this, we define mathematically a relation R from A to B as an arbitrary subset of A into B. If AB belongs to R, we say that A is related to B under the relation R, and we write as A R B. In general, AB belongs to R. We do not bother whether there is a recognizable connection or link between A and B. As seen in class 11, functions are special kind of relations. In this chapter, we will study different types of relations and functions, composition of functions, invertible functions, and binary operations. Types of relations. In this section, we would like to study different types of relations. We know that a relation in a set A is a subset of A into A. Thus, the empty set null, phi, and A into A are two extreme relations. For illustration, consider a relation R in the set A equal to 1, 2, 3, 4 given by R equal to AB, that is A minus B equal to 10. This is the empty set as no pair AB satisfy the condition A minus B equal to 10. Similarly, R dash equal to AB, that is mod of A minus B greater than equal to 0, is the whole set A into A, as all pairs AB in A into A satisfy. Mod of A minus B greater than equal to 0. These two extreme examples lead us to the following definition. Definition 1. A relation R in a set A is called empty relation if no element of A is related to any element of A, that is R equal to phi subset of A into A. Definition 2. A relation R in a set A is called universal relation if each element of A is related to every element of A, that is R equal to A into A. Both the empty relation and the universal relation are sometimes called trivial relations. Example 1. Let A be the set of all students of a boys' school so that the relation R in A given by R equal to AB, that is A is sister of B, is the empty relation, and R dash equal to AB, the difference between heights of A and B is less than 3 meters, is the universal relation. Solution. Since the school is boys' school, no student of the school can be sister of any student of the school. Hence, R equal to 5, showing that R is the empty relation. Null. It is also obvious that the differences between heights of any two students of school has to be less than 3 meters. This shows that R dash equal to A into E is the universal relation. Remark: in class 11, we have seen two ways of representing a relation, namely raster method and set builder method. However, a relation R in the set 1, 2, 3, 4 defined by R equal to AB, that is B equal to A plus 1, is also expressed as ARB if and only if B equal to A plus 1 by many authors. We may also use this notation as and when convenient. If AB belongs to R, we say that A is related to B and we denote it as ARB. One of the most important relations which plays a significant role in mathematics is the equivalence relations. To study equivalence relation, we first consider three types of relations, namely reflexive, symmetric, and transitive. Definition 3. A relation R is a set A is called 1. Reflexive if AA belongs to R for every A belongs to A. 2. Symmetric if A1, A2 belongs to R implies that A2, A1 belongs to R for all A1, A2 belongs to A. 3. Transitive if A1, A2 belongs to R and A2, A3 belongs to R implies that A1, A3 belongs to R for all A1, A2, A3 belongs to A. Definition 4. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric, and transitive. Example 2. Let T be the set of all triangles in a plane with R a relation in T given by R equal to T1, T2. That is, T1 is congruent to T2 shows that R is an equivalence relation. Solution: R is reflexive since every triangle is congruent to itself. Further, T1, T2 belongs to R. T1 is congruent to T2. T2 is congruent to T1. Implies that T2, T1 belongs to R. Hence, R is symmetric. Moreover, T1, T2, T2, T3 belongs to R. That is, T1 is congruent to T2 and T2 is congruent to T3. That is, T1 is congruent to T3. That is, T1, T3 belongs to R. Therefore, R is an equivalence relation. Example 3. Let L be the set of all lines in a plane. R be the relation in L defined as R equal to L1, L2. that is L1 is perpendicular to L2 shows that R is symmetric but neither reflexive nor transitive. Solution: R is not reflexive as a line L1 cannot be perpendicular to itself, that is L1 not belongs to R. R is symmetric as L1 L2 belongs to R, that is L1 is perpendicular to L2, that is L2 is perpendicular to L1, that is L2 L1 belongs to R. Figure L1 L3 L2. R is not transitive indeed if L1 is perpendicular to L2 and L2 is perpendicular to L3. Then L1 can never be perpendicular to L3. In fact, L1 is parallel to L3, that is L1 L2 belongs to R, L2 L3 belongs to R, but L1 L3 not belongs to R. Example 4 show that the relation R in the set 1, 2, 3 given by R equal to 1 1 2 2 3 3 1 2 2 3 is reflexive but neither symmetric nor transitive. Solution: R is reflexive since 1 1 2 2 and 3 3 lie in R. Also R is not symmetric as 1 2 belongs to R but 2 1 not belongs to R. Similarly, R is not transitive as 1 2 belongs to R and 2 3 belongs to R but 1 3 not belongs to R. Example 5 show that the relation R in the set Z of integers given by R equal to AB, that is 2 divides A minus B, is an equivalence relation. Solution: R is reflexive as 2 divides A minus A for all A belongs to Z. Further, if AB belongs to R, then 2 divides A minus B. Therefore, 2 divides B minus A, hence BA belongs to R, which shows that R is symmetric. Similarly, if AB belongs to R and BC belongs to R, then A minus B and B minus C are divisible by 2. Now, A minus C equal to A minus B plus B minus C is even. Why? Comment this. So, A minus C is divisible by 2. This shows that R is transitive. Thus, R is an equivalence relation in Z. In example 5, note that all even integers are related to 0 as 0 plus minus 2, 0 plus minus 4, etc. lie in R, and no odd integer is related to 0 as 0 plus minus 1, 0 plus minus 3, etc. do not lie in R. Similarly, all odd integers are related to 1 and no even integers is related to 1. Therefore, the set E of all even integers and the set O of all odd integers are subsets of Z, satisfying following conditions. 1. All elements of E are related to each other and all elements of O are related to each other. 2. No element of E is related to any element of O and vice versa. 3. E and O are disjoint and Z equal to E union O. The subset E is called the equivalence class containing 0 and is denoted by 0. Similarly, O is the equivalence class containing 1 and is denoted by 1. Note that 0 not equal to 1, 0 equal to 2R and 1 equal to 2R plus 1, R belongs to Z. In fact, what we have seen above is true for an arbitrary equivalence relation R in a set X. Given an arbitrary equivalence relation R in an arbitrary set X, R divides X into mutually disjoint subsets AI called partitions or subdivisions of X satisfying. 1. All elements of AI are related to each other for all I. 2. No element of AI is related to any element of AJ, I not equal to J. 3. union aj equal to x and ai intersection aj equal to phi, null, I not equal to j. The subsets Aj I are called equivalence classes. The interesting part of the situation is that we can go reverse also. For example, consider a subdivision of the set Z given by three mutually disjoint subsets A1, A2 and A3 whose union is Z with A1 equal to x belongs to Z, that is x is a multiple of 3 equal to dot 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 minus 6 minus 3 0 3 6. A2 x belongs to Z, that is x minus 1 is a multiple of 3 equal to minus 5 minus 2 1 4 7. A3 equal to x belongs to J, that is x minus 2 is multiple of 3 equal to minus 4 minus 1 2 5 8. Define a relation R in Z given by R equal to AB, that is 3 divides A minus B. Following the argument similar to those used in example 5, we can show that R is an equivalence relation. Also, A1 coincides with the set of all integers in Z which are related to 0. A2 coincides with the set of all integers which are related to 1, and A3 coincides with the set of all integers in Z which are related to 2. Thus, A1 equal to 0, A2 equal to 1, A3 equal to 2. In fact, A1 equal to 3R, A2 equal to 3R plus 1, A3 equal to 3R plus 2 for all R belongs to Z. Example 6. Let R be the relation defined in the set A 1, 2, 3, 4, 5, 6, 7 by R equal to AB. Both A and B are either odd or even. Show that R is an equivalence relation. Further, show that all elements of subset 1, 3, 5, 7 are related to each other and all the elements of subset 2, 4, 6 are related to each other, but no elements of subset 1, 3, 5, 7 is related to any element of the subset 2, 4, 6. Solution. Given any element A in A, both A and A must be either odd or even, so that A belongs to R. Further, AB belongs to R. Both A and B must be either odd or even, that is BA belongs to R. Similarly, AB belongs to R and BC belongs to R. That is, all elements ABC must be either even or odd simultaneously, that is AC belongs to R. Hence, R is an equivalence relation. Further, all the elements of 1, 3, 5, 7 are related to each other as all the elements of the subsets and odd. Similarly, all the elements of subset 2, 4, 6 are related to each other as all of them are even. Also, no element of the subset 1, 3, 5, 7 can be related to any element of 2, 4, 6 as elements of 1, 3, 5, 7 are odd, while elements of 2, 4, 6 are even. Exercise 1.1. Do this. Types of functions. The notion of a function along with some special function like identity function, constant function, polynomial function, rational function, modulus function, signum function, etc. along with their graphs have been given in class 11. Addition, subtraction, multiplication and division of two functions have also been studied. As the concept of function is of paramount importance in mathematics and among other disciplines as well, we would like to extend our study about function from where we finished earlier. In this section, we would like to study different types of functions. Consider the functions f1, f2, f3 and f4 given by the following diagram. In figure 1.2, we observe that the images of distinct elements of x1 under the function f1 are distinct, but the image of two distinct elements 1 and 2 of x1 under f2 is same, namely b. Further, there are some elements like e and f in x2, which are not images of any element of x1 under f1. While all elements of x3 are images of some elements of x1 under f3, the above observation lead to the following definition. Definition 5. A function f x belongs x to y, x tends to y is defined to be 1, 1 or injective. If the images of distinct element of x under f are distinct, that is for every x1, x2 belongs to x, f x1 equal to f x2 implies x1 equal to x2, otherwise f is called many one. The function f1 and f4 in figure 1 and 4 are 1, 1, and the function f2 and f3 in figure 2 and 3 are many one. Definition 6. A function f, that is x tends to y, said to be onto or surjective. If every element of y is the image of some element of x under f, that is for every y belongs to y, there exists an element x in x such that fx equal to y. The function f3 and f4 in figure 3, 4 and onto and the function f1 in figure 1 is not onto as elements e. F in x2 are not the image of any element in x1 under f1. Figure 1 to 4. 1. x1, x2, 1, 2, 3, 4, a, b, c, d, e, f. f1. 2. x1, x2, f2, 1, 2, 3, 4, a, b, c, d, e, f. 3. x1, x3, f3, 1, 2, 3, 4, a, b, c. 4. x1, x4, f4, 1, 2, 3, 4, a, b, c, d. Remark, f, that is x tends to y, is onto if and only if range of f equal to y. Definition 7. A function f, that is x tends to y, is said to be 1, 1 and 1, 2 or bijective if f is both 1, 1 and onto. The function f4 in figure 4 is 1, 1 and onto. Example 7. Let A be the set of all 50 students of class 10 in a school. Let f, that is a tends to n, be function defined by fx equal to roll number of the student x. Show that f is 1, 1 but not onto. Solution. No two different students of the class can have same roll number, therefore f must be 1, 1. We can assume without any loss of generality the roll numbers of students are from 1 to 50. This implies that 51 in n is not roll number of any student of the class, so that 51 cannot be image of any element of x under f. Hence f is not onto. Example 8. Show that the function f, that is n tends to n, given by fx equal to 2x is 1, 1 but not onto. Solution. The function f is 1, 1 for f x1 equal to f x2, that is 2x1 equal to 2x2, that is x1 equal to x2. Further, f is not onto. As for 1 belongs to n, there does not exist any x in n such that fx equal to 2x equal to 2x equal to 1. Example 9. Prove that the function f, that is r tends to r, given by fx equal to 2x is 1, 1 and onto. Solution. F is 1 1 as fx1 equal to fx2 equal to 2x1 equal to 2x2 equal to x1 equal to x2. Also given any real number in R that exists y by 2 in R such that f of y by 2 equal to 2 into y by 2 equal to y. Hence f is onto. Figure x dash y dash y equal to fx equal to 2x. Example 10, show that the function f, that is n tends to n, given by f1 equal to f2 equal to 1 and fx equal to x minus 1 for every x greater than 2 is onto but not 1 1. Solution. F is not 1 1 as f1 equal to f2 equal to 1, but f is onto as given any y belongs to n, y not equal to 1. We can choose x as y plus 1 such that f of y plus 1 equal to y plus 1 minus 1 equal to y. Also for 1 belongs to n, we have f1 equal to 1. Example 11, show that the function f, that is r tends to r, defined as fx equal to x square, is neither 1 1 nor onto. Solution. Since f minus 1 equal to 1 equal to f1, f is not 1 1. Also the element minus 2 in the codomain R is not image of any element x in the domain R. Why? Comment this. Therefore f is not onto. The image of 1 and minus 1 under f is 1. F x dash y dash, f minus 1 equal to 1, f1 equal to 1, x equal to minus 1, x equal to 1, fx equal to x square. Example 12, show that f, that is n tends to n, given by x plus fx equal to x plus 1 if x is odd, x minus 1 if x is even, is both 1 1 and onto. Solution. Suppose if x1 equal to fx2, note that if x1 is odd and x2 is even, then we will have x1 plus 1 equal to x2 minus 1, that is x2 minus x1 equal to 2, which is impossible. Similarly, the possibility of x1 being even and x2 being odd can also be ruled out using the similar argument. Therefore both x1 x2 must be either odd or even. Suppose both x1 x2 are odd, then f x1 equal to fx2, that is x1 plus 1 equal to x2 plus 1, that is x1 equal to x2. Similarly, if both x1 and x2 are even, then also if x1 equal to fx2, that is x1 minus 1 equal to x2 minus 1, that is x1 equal to x2. Thus f is 1 1. Also any odd number 2r plus 1 in the codomain n is the image of 2r plus 2. In the domain n, and any even number 2r in the codomain n is the image of 2r minus 1 in the domain n. Thus f is onto. Example 13, show that an onto function f, that is 1 2 3 tends to 1 through 3 is always 1 1. Solution. Suppose f is not 1 1, then there exist two elements, say 1 and 2, in the domain whose image in the codomain is same. Also the image of 3 under f can be only one element. Therefore the range set can have at the most two elements of the codomain 1 2 3, showing that f is not onto a contradiction. Hence f must be 1 1. Example 14, show that a 1 1 function f, that is 1 to 3 tends to 1 to 3 must be on 2. Solution. Since f is 1 1, three elements of 1 to 3 must be taken to three different elements of the codomain 1 to 3 under f. Hence f has to be 1 2. Remark: the result mentioned in example 13 and 14 are also true for an arbitrary finite set X. That is, a 1 1 function f that is x tends to x is necessarily onto an onto map f that is x tends to x is necessarily 1 1 for every finite set X. In contrast to this, example 8 and 10 show that for an infinite set this may not be true. In fact, this is a characteristic difference between a finite and an infinite set. Exercise. Do this and comment this. Composition of functions and invertible functions. In this section, we will study composition of functions and the inverse of a bijective function. Consider the set A of all students who appeared in class 10 of a board examination in 2006. Each student appearing in the board examination is assigned a roll number by the board, which is written by the students in the answer script at the time of examination. In order to have confidentiality, the board arranges to deface the roll numbers of students in the answer script and assign a fake code number to each roll number. Let B subset of n be the set of all roll numbers and C subset of n be the set of all code numbers. This gives rise to two functions f that is a tends to b and g that is b tends to c, given by fa equal to the roll number assigned to the student A and gb equal to the code number assigned to the roll number B. In this process, each student is assigned a roll number through the function f, and each roll number is assigned a code number through the function g. Thus, by the combination of these two functions, each student is eventually attached a code number. This leads to the function definition. Definition 8, let f that is a tends to b and g that is b tends to c be two functions, then the composition of f and g denoted by GOF is defined as that function GOF a tends to c given by GOF of x, g of f of x. That is, for all x belongs to a. Figure GOF a f b c f g x g of fx. Example 15, let f 2 3 4 5 that is 3 4 5 9 and g 3 4 5 9 that is 7 11 15 be function defined as f2 equal to 3, f3 equal to 4, f4 equal to 5 and g3 equal to g4 equal to 7 and g5 equal to g9 equal to 11. Find GOF. Solution. We have G of f2 and G of f2 equal to g3 equal to 7. G of f3 equal to G of f3 equal to g4 equal to 7. G of f4 equal to G of f4 equal to g5 equal to 11 and G of f5 equal to g5 equal to 11. Example 16, find GOF and FOG. If f r tends to r and g r tends to r, are given by fx is equal to cos x and gx equal to 3x square, show that GOF not equal to FOG. Solution. We have GOF equal to g of fx equal to g cos x equal to 3 cos x square equal to 3 cos square x. Similarly, f of gx equal to f of gx equal to f of 3x square equal to cos 3x square. Note that 3 cos square x not equal to cos 3x square for x equal to 0, hence GOF not equal to FOG. Example 17, so that if f r minus 7 by 5 tends to r minus 3 by 5 is defined by fx equal to 3x plus 4 by 5x minus 7 and g r minus 3 by 5 tends to r minus 7 by 5 is defined by gx equal to 7x plus 4 by 5x minus 3, then FOG equal to IA and GOF equal to IB, where A equal to r minus 3 by 5, B equal to r minus 7 by 5, IA x equal to x for all x belongs to A, IB x equal to x for all x belongs to B are called identity functions on sets A and B respectively. Solution. We have GOF x equal to g of 3x plus 4 by 5x minus 7 equal to 7 of 3x plus 4 by 5x minus 7 plus 4 by 5 of 3x plus 4 by 5x minus 7 minus 3 equal to 21x plus 28 plus 20x minus 28 by 15x plus 20 minus 15x plus 21 equal to 41x by 41 equal to x. Similarly, f of gx equal to f of 7x plus 4 by 5x minus 3 equal to 3 of 7x plus 4 by 5x minus 3 plus 4 by 5 of 7x plus 4 by 5x minus 3 minus 7 equal to 21x plus 12 plus 20x minus 12 by 35x plus 20 minus 35x plus 21 equal to 41x minus 41x by 41 equal to x. Thus GOF x equal to x for all x belongs to B and FOG x equal to x for all x belongs to A, which implies that GOF equal to IB and for FOG equal to IA. Example 18, show that if F A tends to B and G B tends to C are 1 1, then GOF A tends to C is also 1 1. Solution. Suppose GOF x1 equal to GOF x2, that is g of fx1 equal to g of fx2, fx1 equal to fx2 as g is 1 1, that is x1 equal to x2 as f is 1 1, hence GOF is 1 1. Example 19, show that if f A tends to B and G B tends to C are onto, then GOF A tends to C is also onto. Solution. Given an arbitrary element Z belongs to C, there exists a pre-image Y of Z under G such that Gy equal to Z since G is onto. Further, for Y belongs to B, there exists an element X in A. With fx equal to y, since f is onto, therefore g of x equal to g of fx equal to gy equal to z, showing that GOF is onto. Example 20. Consider functions f and g such that composite GOF is defined and is 1 1, f and g both necessarily 1 1. Solution. Consider f 1 2 3 4 tends to 1 2 3 4 5 6 defined as fx equal to x for all x and g 1 2 3 4 5 6 tends to 1 2 3 4 5 6 as gx equal to x for x equal to 1, 2, 3, 4 and g5 equal to g6 equal to 5. Then g of x equal to x for all x, which shows that g of is 1, 1, but g is clearly not 1, 1. Example 21, are f and g both necessarily onto? If g of is onto, solution, consider f 1, 2, 3, 4 tends to 1, 2, 3, 4 and g 1, 2, 3, 4 tends to 1, 2, 3 defined as f1 equal to 1, f2 equal to 2, f3 equal to f4 equal to 3, g1 equal to 1, g2 equal to 2 and g3 equal to g4 equal to 3. It can be seen that g of is onto but f is not onto. Remark, it can be verified is general that g of is 1, 1 implies that f is 1, 1. Similarly, g of is onto implies that g is onto. Now we would like to have close look at the functions f and g described in the beginning of this section in reference to a board examination. A student appearing in class 10 examination of the board is assigned a roll number under the function f, and each roll number is assigned a code number under g. After the answer scripts are examined, examiner enters the mark against each code number in a mark book and submits to the office of the board. The board official decode by assigning roll number back to each code number through a process reverse to G, and thus marks get attached to roll number rather than code number. Further, the process reverse to F assigns a roll number to the student having that roll number. This helps in assigning mark to the student scoring that mark. We observe that while composing f and g to get g of first f and then g was applied, while in the reverse process of the composite g of first the reverse process of g is applied and then the reverse process of f. Example 22, let f 1, 2, 3 tends to ABC be 1, 1 and onto function given by f1 equal to a, f2 equal to b, f3 equal to c. Show that there exists a function g abc tends to 1 to 3 such that g of f equal to yx and f of g equal to y, where x equal to 1 to 3 and y equal to abc. Solution. Say consider g ABC tends to 1 to 3 and GA equal to 1, GB equal to 2 and GC equal to 3. It is easy to verify that the composite GA equal to YX is the identity function on X and the composite FOG IY is the identity function on Y. Remark, the interesting fact is that the result mentioned in the above example is true for an arbitrary 1, 1 and onto function f x tends to y. Not only this, even the converse is also true, that is, if f x tends to y is a function such that there exists a function g y tends to x such that g of f equal to ix and f of g equal to iy, then f must be 1, 1 and onto. The above discussion, example 22 and remark led to the following definition. Definition 9. A function f x tends to y is defined to be invertible if there exists a function g y tends to x such that g of f equal to ix and f of g equal to iy. The function g is called the inverse of f and is denoted by f inverse. Thus, if f is invertible, then f must be 1, 1 and onto, and conversely, if f is 1, 1 and onto, then f must be invertible. This fact significantly helps for proving a function f to be invertible by showing that f is 1, 1 and onto, especially when the actual inverse of f is not to be determined. Example 23, let f n tends to y be a function defined as fx equal to 4x plus 3, where y equal to y belongs to n, y equal to 4x plus 3 for some x belongs to n. So that f is invertible. Find the inverse. Solution. Consider an arbitrary element y of y by the definition y equal to 4x plus 3 for some x in the domain n. This shows that x equal to y minus 3 by 4 define g y belongs to n by gy equal to y3 minus y minus 3 by 4. Now g of x equal to g of fx equal to g of 4x plus 3 equal to 4x plus 3 minus 3 by 4 equal to x, and f of gy equal to f of gy equal to f of y minus 3 by 4 equal to 4 of y minus 3 by 4 plus 3 equal to y minus 3 plus 3 equal to y. This shows that g of equal to yn and f of g equal to y, which implies that f is invertible and g is the inverse of f. Example 24, let y equal to n square, n belongs to n, subset of n, consider f n tends to y as fn equal to n square, so that f is invertible. Find the inverse of f. Solution. An arbitrary element y in y is of the form n square for some n belongs to n. This implies that n equal to root of x. This gives a function g y tends to n defined by gy equal to root y. Now g of n equal to g of n square equal to root n square equal to n. F of gy equal to f of y square, f of root y equal to root y whole square equal to y, which shows that g of equal to in and f of g equal to iy. Hence f is invertible with f inverse equal to g. Example 25, let f dash n tends to r be a function defined as f dash x equal to 4x square plus 12x plus 15, so that f n tends to s, where s is the range of f, is invertible. Find the inverse of f. Solution. Let y be an arbitrary element of range f, then y equal to 4x square plus 12x plus 15 for some x in n, which implies that y equal to 2x plus 3 whole square plus 6. This gives x equal to root over y minus x minus 3 by 2 as y greater than equal to 6. Let us define g s tends to n by gy equal to root over y minus 6 minus 3 by 2. Now g of x equal to g of fx, g of 4x square plus 12x plus 15 equal to g of 2x plus 3 whole square plus 6 equal to root 2x plus 3 whole square plus 6 minus 3 by 2 equal to 2x plus 3 minus 3 by 2 equal to x. And f of gy equal to f of root y minus 6 minus 3 by 2 equal to 2 of root y minus 6 minus 3 by 2 plus 3 whole square plus 6 equal to root y minus 6 minus 3 plus 3 whole square plus 6 equal to root y minus 6 whole square plus 6 equal to y minus 6 plus 6 equal to y. Hence g of f equal to yn equal to f of g equal to is. This implies that f is invertible with f inverse equal to g. Example 24. Consider f n tends to n, g n tends to n, and h n tends to r defined as fx equal to 2x, gy equal to 3y plus 4, hz equal to sin z for all x, y, and z in n. Show that ho g of f and ho g of f. Solution. We have ho g of f x, h g of f x, h of g of fx equal to h of g of 2x equal to h of 3 of 2x plus 4 equal to h of 6x plus 4 equal to sine of 6x plus 4 for all x belongs to n. Also, h of g of x equal to h of g fx equal to h of g 2x equal to h of g of 2x. H of 3 of 2x plus 4 equal to h of 6x plus 4 sine 6x plus 4 for all x belongs to n. This shows that HOGOF, this result is true in general situation as well. Theorem 1, if x tends to y, y tends to z, and z tends to s are function, then HOGOF equal to HOGOF. Proof. We have HOGOF x equal to HGOFX equal to HGFX for all x in x. And HOG of x, HOGFX, H of GFX for all x in x. Hence, HOGOF, HOGOF. Example 27. Consider F1 to 3 tends to ABC and G, YBC, apple, ball, cat, defined as F1 equal to A, F2 equal to B, F3 equal to C, GA equal to apple, GB equal to ball, and GC equal to cat. So that F, G, and GOF are invertible, find out F inverse, G inverse, and GOF inverse, and show that GOF inverse equal to F inverse or G inverse. Solution. Note that by definition F and G are bijective function. Let F inverse ABC tends to 1 to 3 and G inverse apple, ball, cat tends to ABC be defined as F inverse A equal to 1, F inverse B equal to 2, F inverse C equal to 3, G inverse apple equal to A, G inverse ball equal to B, and G inverse cat equal to C. It is easy to verify that F inverse OF equal to Y 1 to 3, F inverse equal to Y ABC, G inverse OG equal to I ABC, and G inverse equal to ID. Where D equal to apple, ball, cat, now GOF 1 to 3 apple, ball, cat is given by GOF 1 apple, GOF 2 equal to ball, GOF 3 equal to cat. We can define GOF inverse apple, ball, cat tends to 1 to 3 by GOF inverse apple equal to 1, GOF inverse ball equal to 2, and GOF inverse cat equal to 3. Is easy to see that GOF inverse or GOF equal to Y 1 to 3 and GOF or GOF inverse equal to YD. Thus, we have seen that FG and GOF are invertible. Now, F inverse or G inverse equal to apple equal to apple equal to F inverse G inverse apple equal to F inverse A equal to 1 equal to GOF inverse apple. F inverse or G inverse ball equal to F inverse of G inverse of ball equal to F inverse of B equal to 2 GOF inverse of ball, and F inverse or G inverse of cat equal to F inverse of G inverse cat equal to F inverse C equal to 3 GOF inverse cat. Hence, GOF inverse equal to F inverse or G inverse. The above result is true in general situation also. Next, theorem 2, let f of x tends to y and y tends to z be two invertible functions, then GOF is also invertible with GOF inverse equal to F inverse or G inverse. Proof. To show that GOF is invertible with GOF inverse equal to F inverse or G inverse, it is enough to show that F inverse or G inverse or GOF equal to IX and GOF or F inverse or G inverse equal to IZ. Now, F inverse or G inverse or GOF equal to F inverse or G inverse OG of by theorem 1 equal to F inverse O G inverse OG of by theorem 1 equal to F inverse O IY of by definition of G inverse equal to IX. Similarly, it can be shown that GOF O F inverse O G inverse equal to IZ. Example 38. Let S equal to 1 to 3. Determine whether the function f tends to S defined as below have inverses. Find F inverse if it exists. A. F 1 1 2 2 3 3. B. F 1 2 2 1 3 1. C. F 1 3 3 2 2 1. Solution. A. It is easy to see that F is 1, 1 and 1, 2. So that F is invertible with the inverse F inverse of F given by F inverse equal to 1, 1, 2, 2, 3, 3 equal to F. B. Since F2 equal to F3 equal to 1, F is not 1, 1, so that F is not invertible. C. It is easy to see that F is 1, 1 and 1, 2, so that F is invertible with F inverse 3, 1, 2, 3, 1, 2. Exercise. Do this and comment this. Binary operations. Right from the school days, you must have come across four fundamental operations, namely addition, subtraction, multiplication, and division. The main feature of this operation is that given any two numbers a and b, we associate another number a plus b or a minus b or a b or a by b. B not equal to 0. It is to be noted that only two numbers can be added or multiplied at a time. When we need to add three numbers, we first add two numbers and the result is then added to the third number. Thus, addition, multiplication, subtraction, and division are examples of binary operation, as binary means two. If we want to have a general definition which can cover all these four operations, then the set of numbers is to be replaced by an arbitrary set x, and then general binary operation is nothing but association of any pair of elements ab from x to another element of x. This gives rise to a general definition as follows. Definition 10. A binary operation asterisk on a set A is a function asterisk A into A tends to A. We denote asterisk AB by A asterisk B. Example 29. Show that addition, subtraction and multiplication are binary operation on R, but division is not a binary operation on R. Further, show that division is a binary operation on the set R of non-zero real numbers. Solutions. Plus R into R tends to R is given by AB tends to A plus B, minus R into R tends to R is given by AB tends to A minus B. Cross R into R tends to R is given by AB tends to AB. Since plus, minus and cross are function, they are binary operation on R, but division R into R tends to R given by AB tends to A by B is not a function and hence not a binary operation, as for B equal to 0, A by B is not defined. However, divide R in R asterisk into R asterisk tends to R asterisk given by AB tends to A by B is a function and hence a binary operation on R. Example 30. Show that subtraction and division are not binary operation on N. Solution. Subtraction. N into A tends to N given by AB tends to A minus B is not binary operation, as the image of 3, 5. Under subtraction is 3 minus 5 equal to minus 2, not belongs to N. Similarly, divide N into N tends to N given by AB tends to A by B is not a binary operation, as the image of 3, 5 under divide is 3 divide 5 equal to 3 by 5 not belongs to N. Example 31. So that asterisk R into R tends to R given by AB tends to A plus 4B square is a binary operation. Solution. Since asterisk carries each pair AB to a unique element A plus 4B square in R, asterisk is a binary operation on R. Example 32. Let P be the set of all subset of a given set X, so that union P into P tends to P given by AB, that is A union B, and intersection P into P, that is P given by AB, that tends to A intersection B, are binary operation on the set P. Solution: since union operation, union carries each pair AB in P into P to a unique element A union B. In P, union is a binary operation on P. Similarly, the intersection operation, intersection carries each pair AB in P into P to a unique element A intersection B. In P, intersection is a binary operation on P. Example 33 show that the OR R into R tends to R given by AB tends to max AB, and the OR and R into R tends to R given by AB, that is min AB, are binary operations. Solution: since OR carries each pair AB in R into R to a unique element, namely maximum of A and B lying in R, OR is a binary operation. Using the similar argument, on can say that AND is also a binary operation. Remark: or 4 7 equal to 7, or 4 minus 7 equal to 4, or and 4 7 equal to 4, and 4 minus 7 minus 7. When number of element in a set A is small, we can express a binary operation asterisk on the set A through a table called the operation table for the operation asterisk. For example, consider A 1 2 3, then the operation OR on A defined in example 33 can be expressed by the following operation table here, or 1 3 3, or 2 3 3, or 1 2 2. Table B 1 2 3 1 2 3 1 1 1 2 1 2 3 1 3 1 2 2 2 2 2 3 2 3 1 3 3 2 3 3 3 3 3. Here we are having 3 rows and 3 columns in the operation table with ij, the entry of the table being maximum of ith and jth element of the set A. This can be generalized for general operation asterisk A into A tends to A. If A equal to A1, A2, dot 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 n, then the operation table will be having n rows and n columns with ij entry being ai asterisk aj. Conversely, given any operation table having n rows and n columns with each entry being an element of A equal to A1, A2, dot 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 n, we can define a binary operation asterisk A into A tends to A given by AI asterisk aj, the equal to the entry in the ith row and jth column of the operation table. One may note that 3 and 4 can be added in any order and the result is same, that is 3 plus 4 equal to 4 plus 3, but subtraction of 3 and 4 in different order gives different result. That is 3 minus 4 not equal to 4 minus 3. Similarly, in case of multiplication of 3 and 4, order is immaterial, but division of 3 and 4 in different order give different result. Thus, addition and multiplication of 3 and 4 are meaningful, but subtraction and division of 3 and 4 are meaningless. For subtraction and division, we have to write subtract 3 from 4, subtract 4 from 3, divide 3 by 4, or divide 4 by 3. This leads to the following definition. Definition 11. A binary operation asterisk on the set X is called commutative if A asterisk B equal to B asterisk A for every AB belongs to X. Example 34. So that plus R into R tends to R, and cross R into R tends to R are commutative binary operation, but minus R into R tends to R and division R into R tends to R are not commutative. Solution: since a plus b equal to b plus a and a into b equal to b into a, for all ab belongs to R, plus and cross are commutative binary operation. However, minus is not commutative since 3 minus 4 not equal to 4 minus 3. Similarly, 3 divided 4 not equal to 4 divided 3 shows that divide is not commutative. Example 35, so that asterisk R into R tends to R defined as A asterisk B equal to A plus 2B is not commutative. Solution: since 3 asterisk 4 equal to 3 plus 8 equal to 11 and 4 asterisk 3 equal to 4 plus 6 equal to 10, showing that the operation asterisk is not commutative. If we want to associate three elements of a set X through a binary operation on X, we encounter a natural problem. The expression A asterisk B asterisk C may be interpreted as A asterisk B asterisk C or A asterisk B asterisk C, and these two expressions need not be same. For example, 8 minus 5 minus 2 not equal to 8 minus 5 minus 2. Therefore, association of three numbers 8, 5 and 3 through the binary operation subtraction is meaningless unless bracket is used, but in case of addition 8 plus 5 plus 2 has the same value whether we look at it as 8 plus 5 plus 2 or as 8 plus 5 plus 2. The association of 3 or even more than 3 numbers through addition is meaningful without using bracket. This leads to the following. Definition 12. A binary operation asterisk A into A is said to be associative if A asterisk B asterisk C equal to A asterisk B asterisk C for all A, B, C belongs to A. Example 36. So that addition and multiplication are associative binary operation on R, but subtraction is not associative on R. Division is not associative on R. Solution: addition and multiplication are associative since A plus B plus C equal to A plus B plus C and A into B into C and A into B into C for all ABC belongs to R. However, subtraction and division are not associative as 8 minus 5 minus 3 not equal to 8 minus 5 minus 3 and 8 divide 5 divide 3 not equal to 8 divide 5 divide 3. Example 37, so that asterisk R into R tends to R given by A asterisk B tends to A plus B to B is not associative. Solution: the operation asterisk is not associative since 8 asterisk 5 asterisk 3 equal to 8 plus 10 asterisk 3 equal to 8 plus 10 plus 6 equal to 24, while 8 asterisk 5 asterisk 3 equal to 8 asterisk 5 plus 6 equal to 8 asterisk 11 equal to 8 plus 22 equal to 30. Remark: associative property of a binary operation is very important in the sense that with this property of a binary operation we can write a1 asterisk a2 asterisk dot 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 asterisk an, which is not ambiguous, but in absence of this property the expression a1 asterisk a2 asterisk dot 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 asterisk an is ambiguous unless brackets are used. Recall that in the earlier classes, brackets were used whenever subtraction or division operations or more than one operations occurred. For the binary plus operation plus on R, the interesting feature of the number 0 is that a plus 0 equal to a equal to 0 plus a. That is, any number remains unaltered by adding 0, but in case of multiplication, the number 1 plays this role as a into 1, a equal to 1 into a for all a in R. This leads to the following definition. Definition 13. Given a binary operation asterisk a into a tends to a, an element it belongs to a if it exists is called identity for the operation asterisk e. If a asterisk c equal to e asterisk a for all A belongs to A. Example 38 show that 0 is the identity for addition on R and 1 is the identity for multiplication on R, but there is no identity element for the operation. Minus R into R tends to R and divide R into R tends to R. Solution: A plus 0 equal to 0 plus A equal to A into 1 equal to A equal to 1 into A. For all A belongs to R implies that 0 and 1 are identity elements for the operation plus and cross respectively. Further, there is no element E in R with A minus E equal to E minus A for all A. Similarly, we cannot find any element E in R such that A divide E equal to E divide A for all A in R. Hence, minus and divide do not have identity element. Remark: 0 is identity for the addition operation on R, but it is not identity for the addition operation on N, as 0 not belongs to N. In fact, the addition operation on N does not have any identity. One further notice that for the addition operation plus R into R tends to R, given any A belongs to R, there exists minus A in R such that A plus minus A equal to 0. Identity for plus and minus A plus 1. Similarly, for the multiplication operation on R, given any A not equal to 0 in R, we can choose 1 by A in R such that A into 1 by A equal to 1, identity for cross, equal to 1 by A equal to into A. This leads to the following definition. Definition 14. Given a binary operation asterisk A into A tends to A with the identity element E in A, an element A belongs to A is said to be invertible with respect to the operation asterisk if there exists an element B in A such that A asterisk B equal to E equal to B asterisk A, and B is called the inverse of A and is denoted by A inverse. Example 39 show that minus A is the inverse of A for the addition operation plus on R, and 1 by A is the inverse of A not equal to 0 for the multiplication operations cross on R. Solution: as A plus minus A equal to A minus A equal to 0 and minus A plus A equal to 0, minus A is the inverse of A for addition. Similarly, for A not equal to 0, A into 1 by A equal to 1 into 1 by A into A implies that 1 by A is the inverse of A for multiplication. Example 40 show that minus A is not the inverse of A belongs to N for the addition operation plus on N, and 1 by A is not the inverse of A belongs to N for multiplication operation cross on N for A not equal to 1. Solution: since minus A not belongs to N, minus A cannot be inverse of A for addition operation on N. Although minus A satisfies A plus minus A equal to 0 equal to minus A plus A. Similarly, for A not equal to 1 in N, 1 by A belongs to N, which implies that other than 1, no element of N has inverse for multiplication operation on N. Example 34, 36, 38 and 39 shows that addition on R is a commutative and associative binary operation with 0 as the identity element and minus A as the inverse of A in R for all A. Exercise: comment this and do this. Miscellaneous examples: example 41, if R1 and R2 are equivalence relations in a set A, shows that R1 intersection R2 is also an equivalence relation. Solution: since R1 and R2 are equivalence relations, AA belongs to R1 and AA belongs to R2 for all A belongs to A. This implies that AA belongs to R1 intersection R2 for all A, showing R1 intersection R2 is reflexive. Further, AB belongs to R1 intersection R2 belongs to AB intersection R1 and AB belongs to R2 implies that BA belongs to R1 and BA belongs to R2, that is BA belongs to R1 intersection R2, hence R1 intersection R2 is symmetric. Similarly, AB belongs to R1 intersection R2 and BC belongs to R1 intersection R2, that is AC belongs to R1 and AC belongs to R1, that is AC belongs to R1 intersection R2. This shows that R1 intersection R2 is transitive, thus R1 intersection R2 is an equivalence relation. Example 42, solution. Let R be a relation on the set A of ordered pairs of positive integers defined by x, y, r, u, v if and only if x, v equal to y, u, so that R is an equivalence in relations. Solution. Clearly x, y, r, x, y for all xy belongs to A, since xy equal to yx, this shows that R is reflexive. Further, xy are uv, that is xv equal to yu and uy equal to vx, and hence uv are xy. This shows that R is symmetric. Similarly, xy are uv and uv are ab, that is xv equal to yu and uv equal to va, that is xv of a by u equal to yu of a by u, that is xv of b by v equal to yu of a by u, that is xv equal to ya, and hence xy are ab, thus R is transitive, thus R is an equivalence relations. Example 43, let x 1, 2, 3, 4, 5, 6, 7, 8, 9, let R1 be a relation in x given by R1, xy, x minus y is divisible by 3, and R2 be another relation on x given by R2, xy, xy subset of 147, or xy subset 258, or xy subset 369, shows that R1 equal to R2. Solution. Note that the characteristics of sets 147, 258 and 369 is that difference between any two elements of these sets is a multiple of 3. Therefore, xy belongs to R implies that x minus 1 is a multiple of 3. xy subset 147 or xy subset 258 or xy subset 369, xy, that is xy belongs to R2, hence R1 subset R. Similarly, xy belongs to R2, that is xy subset 147 or xy subset 258 or xy subset 369, that is x minus y is divisible by 3, xy belongs to R1. This shows that R2 subset R1, hence R1 equal to R2. Example 44, let f x tends to y be a function, define a relation R in x given by R equal to AB, FA equal to FB, examine whether R is an equivalence relation or not. Solution. For every A belongs to X, A belongs to R, since FA equal to FA, showing that R is reflexive. Similarity, AB belongs to R implies that FA equal to FB implies that FB equal to FA implies that BA belongs to R. Therefore, R is symmetric. Further, AB belongs to R and BC belongs to R. That is, FA equal to FB and FB equal to FC implies that FA equal to FC implies that AC belongs to R, which implies that R is transitive. Hence, R is an equivalence relation. Example 45, determine which of the following binary operations on the set R are associative and which are commutative. A asterisk B equal to 1 for all AB belongs to R. B, A asterisk B equal to A plus B by 2 for all AB belongs to R. Solution. A, clearly by definition A asterisk B equal to B asterisk A equal to 1 for all AB belongs to R. Also, A asterisk B asterisk C equal to 1 asterisk C equal to 1 and a asterisk b asterisk c equal to a asterisk 1 equal to 1. For all a, b, c belongs to R, hence R is both associative and commutative. B. A asterisk b equal to a plus b by 2 equal to b plus a by 2 equal to b asterisk a. So that asterisk is commutative further. A asterisk b asterisk c equal to a plus b by 2 asterisk c equal to a plus b by 2 plus c by 2 equal to a plus b plus 2c by 4. But a asterisk b asterisk c equal to a asterisk b plus c by 2 equal to a plus b plus c by 2 by 2 equal to 2a plus b plus c by 4 not equal to a plus b plus 2c by 4 is general. Hence asterisk is not associative. Example 46. Find the number of all 1-1 function from set A equal to 1 to 3 to itself. Solution. 1-1 function from 1 to 3 to itself is simply a permutation on 3 symbols 1 to 3. Therefore, total number of 1-1 maps from 1 to 3 to itself is same as total number of permutation on 3 symbols 1 to 3, which is 3 permutation equal to 6. Example 47, let A equal to 1 to 3, then so that the number of relations containing 1, 2 and 2, 3 which are reflexive and transitive but not symmetric is 3. Solution. The smallest relation R1 containing 1, 2 and 2, 3 which is reflexive and transitive but not symmetric is 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 1, 3. Now if we add the pair 2, 1 to R1 to get R2, then the relation R2 will be reflexive, transitive but not symmetric. Similarly, we can obtain R3 by adding 3, 2 to R1 to get the desired relation. However, we can not added two pair 2, 1, 3, 2 or single pair 3, 1 to R1 at a time, as by doing so we will be forced to add the remaining pair in order to maintain transitivity, and in the process the relation will become symmetric also, which is not required. Thus the total number of desired relation is 3. Example 48, so that the number of equivalence relation in the set 1 to 3 containing 1, 2 and 2, 1 is 2. Solution. The smallest equivalence relation R1 containing 1, 2 and 2, 1 is 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. Now we are left with only 4 pairs, namely 2, 3, 3, 2, 1, 3 and 3, 1. If we add any one, say 2, 3, 2, R1, then for symmetry we must add 3, 2 also, and now for transitivity we are forced to add 1, 3 and 3, 1. Thus the only equivalence relation bigger than R1 is the universal relation. This shows that the total number of equivalence relations containing 1, 2 and 2, 1 is 2. Example 49 shows that the number of binary operations are 1, 2 having 1 as identity and having 2 as the inverse of 2 is exactly 1. Solution. A binary operations asterisk on 1, 2 is a function from 1, 2 cross 1, 2 to 1, 2, that is a function from 1, 1, 1, 2 to 1, 2, 2, that is 1, 2, since 1 is the identity for the desired binary operation asterisk. Asterisk 1, 1 equal to 1, asterisk 1, 2 equal to 2, asterisk 2, 1 equal to 2, and the only choice left is for the pair 2, 2. Since 2 is the inverse of 2, that is 2, 2 must be equal to 1, thus the number of desired binary operation is only 1. Example 50, consider the identity function in n tends to n defined as in x equal to x for all x belongs to n. Show that although in is onto, but in plus in, that is n tends to n defined as in plus in x equal to in x plus in x equal to x plus x equal to 2x is not onto. Solution. Clearly in is onto, but in plus in is not onto, as we can find an element 3 in the codomain n such that there does not exist any x in the domain n with in plus in x 2x equal to 2x equal to 3. Example 51, consider a function f 0 pi by 2 tends to r given by fx equal to sin x, and g 0 pi by 2 tends to r given by gx equal to cos x. Show that f and g are 1 1, but f plus g is not 1 1. Solution: since for any two distinct element x1 and x2 in 0 pi by 2 sin x1 not equal to sin x2 and cos x1 not equal to cos x2, both f and g must be 1 1, but f plus g 0 equal to sin 0 plus cos 0 equal to 1, and f plus g pi by 2 equal to sin pi by 2 plus cos pi by 2 equal to 1. Therefore f plus g is not 1 1. Miscellaneous exercise on chapter 1. Do this and comment this. Summary. In this chapter, we studied different types of relation and equivalence relation, composition of functions, invertible functions, and binary operations. The main features of these chapters are as follows. Empty relations. Is the relation R in X given by R equal to null, subset of X into X? Universal relations. Is the relation R in X given by R equal to X into X? Reflexive relation R in X is a relation with A belongs to R for all A belongs to X. Symmetric relation R in X is a relation satisfying AB, that is R implies BA belongs to R. Transitive relation R in X is a relation satisfying AB belongs to R and BC belongs to R, implies that AC belongs to R. Equivalence relation R in X is a relation which is reflexive, symmetric, and transitive. Equivalence class A containing A belongs to X for an equivalence relation R in X is the subset of X containing all elements to be related to A. A function f x tends to y is 1 1 or injective if fx1 equal to fx2 implies that x1 equal to x2 for all x2 belongs to x. A function f x tends to y is onto or surjective if given any y belongs to y that exists x belongs to x such that fx equal to y. A function f x tends to y is 1 1 and onto or bijective if f is both 1 1 and onto. The composition of function f a tends to b and g b tends to c is the function g of f a tends to c given by g of fx g of f of x for all x belongs to a. A function f x tends to y is invertible if for x is g, y tends to x such that g of f equal to ix and f of g equal to iy. A function f x tends to y is invertible if and only if is 1 1 and onto. Given a finite set x, a function of f x tends to x is 1 1 respectively onto if and only if f is onto respectively 1 1. This is characteristic property of a finite set. This is not true for infinite set. A binary operation asterisk on a set A is function asterisk from A into A to A. An element E belongs to X is the identity. Element for binary operation asterisk X into X belongs to X if A asterisk E equal to A equal to E asterisk A not for all A belongs to X. An element A belongs to X is invertible for binary operation asterisk x into x belongs to x if there exists b belongs to x, such that a asterisk b equal to e equal to b asterisk a, where e is the identity for the binary operation asterisk. The element b is called inverse of A and is denoted by A inverse. An operation asterisk on X is commutative if A asterisk B equal to B asterisk A for all AB in X. An operation asterisk on X is associative if A asterisk B asterisk C equal to A asterisk B asterisk C for all A, B, C in X. Historical note. The concept of function has evolved over a long period of time starting from R. Descartes, 1596 to 1650, who used the word function in his manuscript Geometry in 1637 to mean some positive integral power x to the power n of a variable x while studying geometrical curves like hyperbola, parabola, and ellipse. James Gregory, 1636 to 1675, in his work Vera Circuli et Hyperboli Quadratura, 1667, considered function as a quantity obtained from other quantities by successive use of algebraic operation or by any other operation. Later, J. W. Leibniz, 1646 to 1716, in his manuscript Methodas Tangentium Inversa Seu de Functionibus, written in 1673, used the word function to mean a quantity varying from point to point on a curve, such as the coordinates of a point on the curve, the slope of the curve, the tangent, and the normal to the curve at a point. However, in this manuscript Historia 1714, Leibniz used the word function to mean quantities that depend on a variable. He was the first to use the phrase function of x. John Bernoulli, 1667 to 1748, used the notation phi x means null for the first time in 1718 to indicate a function of x, but the general adoption of symbol like f, capital F, phi, psi to represent function was made by Leonhard Euler, 1707 to 1783. In 1734, in the first part of his manuscript Analysis Infinitorium, later on Joseph Louis Lagrange, 1736 to 1813, published his manuscript Theory des Fonctions Analyticus in 1793, where he discussed about analytic function and used the notion fx, capital Fx, phi x, etc. means null x for different function of x. Subsequently, Lejeune Dirichlet 1805 to 1859 gave the definition of function which was being used till the set theoretic definition of function presently used was given after set theory was developed by George Cantor 1845 to 1918. The set theoretic definition of function known to us presently is simply an abstraction of the definition given by Dirichlet in a rigorous manner.